Good.
All right. These are what are called optimization problems.
Optimization problems.
Yeah, and I'm trying to think of the term, linear programming is what this is called.
Linear.
Mm-hmm.
Okay.
Now, oddly enough, this is the very first thing they start off on in Algebra 2. And like most maths, it's the hardest thing in Algebra 2.
Ugh.
Same thing with calculus. They start you off on the hardest thing. Same thing with geometry. They start you off on proofs, the hardest thing. I've never understood why math is taught that way, but it is. I suppose it might have to do with the fact that they're trying to teach students real life applications of this algebra. And that's what these are. In other words, these are real life. In other words, there truly is a merchant out there that sells two different types of computers, and he's trying to figure out which ones to stock. Okay?
Okay. Yes, sir.
So it's definitely a real life problem, and I think I want to do it this way so I can write it out. Yeah, let's do it this way. And let me move that up as high as I can. Only problem with this, I can only get it started. Linear programming problems start out with what is called an objective function.
Yes, sir.
With constraints.
And an objective function with
yeah, the objective function is an equation that you're trying to optimize, and the constraints are usually inequalities. They're not equations.
Inequalities.
Yeah. And the way to solve these, oddly enough, is graphically. And let's do one, and you'll understand, I think, once we do one. Trying to create as much room as I can so that I can write this. The very first thing you need to do is define your variables. So let's do that. Read the problem, and usually the variables you get from the very last sentence.
All right.
Let's look at the last sentence. Find the number of units of each model that should be stocked in order to maximize profit.
All right.
So what are my variables going to be?
So X and Y for the two models?
Yeah. So X would be, and it wants the number of units. So be very specific when you're defining your variables.
Okay.
Is the number of $250 computers. Y would be the number of $400 computers. That's your choice. You're running this business. You want to know how many $250 ones to buy and how many $400 ones to buy.
Yes, sir.
Okay.
Yes, sir.
Now, let's talk about the objective function. because what it wants to know is how do you maximize your profit, right?
Yes, sir.
So we need a profit function.
Okay.
We'll call it P. What is the profit function?
What does it mean by objective function?
Well, I think the best way for me to explain it is to do this problem. And then
Okay.
we'll talk about it in reverse.
Yes,
Because
sir.
objective function by itself doesn't give you a clue as to what it means. What it really means is the function you're trying to maximize or minimize.
Okay.
And in this case, it's profit, right?
That's right.
That's your objective function. So
Yes, sir.
what is the profit function? I make
So that's going to,
$45 profit on my $250 models. I make a $50 profit on my $400 models. So what's my total profit going to be in terms of X and Y?
so it's going to be 45x plus 50y.
Perfect. That's what we want to optimize. Okay?
Yes, sir.
Now, obviously, X being infinity and Y being infinity would maximize the profit, right?
Yes, sir.
But we can't let that be infinity because there are some constraints. Let's see if I can write these constraints without having to rewrite everything. I'm going to have to rewrite everything momentarily anyway, but okay. The merchant estimates that the total monthly demand will not exceed 250 units. Can you give me an inequality that satisfies that sentence?
So would that be x plus y is less than or equal to 250?
Perfect. Now, I'm going to have to erase this to even. That last sentence, what kind of constraint does that give you?
So that means 400x, or was it
I think it's 250.
250x plus 400y has to be less than or equal to 70,000.
So we have an objective function and we have two constraining inequalities.
Yes, sir.
Okay, so let's do this because I need the whole page to write. So our objective function is the profit function.
Yes, sir.
Hold on. So that's profit, and that was equal to 45x plus 50y, right?
Yes, sir.
Okay. And then we had x plus y had to be less than or equal to what? Do you remember?
Was it 250? 250 units?
Unfortunately, I can't switch back and forth. Once I put it in writing mode, I can't leave it without losing everything I've written.
So I think it was 250 units.
Okay. And then we had 45x plus 50y. No, excuse me.
It was 250x plus 400y is less than 70,000.
Yeah, he's got to buy these computers to stock them.
Yes, sir.
And he didn't want to spend over 70,000. Okay. So here's our optimization problem right there. We have a function we want to maximize, and we have these two constraints.
Yes, sir.
Here's how you handle it. You graph everything, actually, you don't graph everything. You graph your two constraining functions. So if I graph that, I get y is less than or equal to negative x plus 250.
Yes, sir.
Well, that's a slope of negative 1
That's right.
that goes through the y-intercept of 250. In other words, that's 250 right there on the y-axis.
Yes, sir.
And that's the slope of that line. That is x plus y is less than or equal to 250, and I'm going to shade the lower left part of that because it has to be less than that.
Yes, sir.
Okay?
And
Now,
it's a solid line.
graph this function,
Yes, sir.
and that function is going to graph a little more difficultly. Let's see, that's minus 250x plus 70,000, all divided by 400. So it's minus 25/40th x plus 7,000. So all I did was just take off a 0.
Yes, sir.
Okay.
That's right.
Well, that's a negative slope. It's not a negative 1 slope. It's a little flatter. And it goes through a much higher 7,000 instead of 250.
7,000 over 40. Not just 7,000.
Yeah, thank you very much.
So
that goes through the point 175.
Yes.
The y-intercept is 175. Okay?
That's
right. A little bit of a flatter slope. We're going to draw that slope like this. Okay?
Yes, sir.
And its y is less than or equal to that. So
yes, sir.
I'm shading the lower left also. So our feasibility region is right there.
Yes, sir.
Our optimum answer is going to come either there, 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 or there. One of those 4 vertices.
Okay, it's at the vertice. Why is it at the vertices?
I'm not sure I can answer that. I just know that your maximum value comes at one of those vertices. And
yes, sir.
The next step is to plug all of them in. And whichever one gives you the highest P is the answer.
Okay.
Okay, it's relatively straightforward. Now, sometimes you can have, instead of 2 constraints, you might have 4 constraints, which gives you a more complicated looking diagram. But your optimized answer is always at one of the vertices.
Yes, sir.
Okay, so let's figure out what the profit is right there. Here, let me use a different color.
At the origin, it will always be 0, right?
Well, in this case, yeah. I can't recall seeing a problem where your optimum was at the origin, although sometimes these are minimizing problems. They're not maximizing. Sometimes you're trying to minimize costs. And
yes, sir.
so it's not impossible that your answer could be at the origin. But clearly, P of 0, 0 is 0. Okay? This is actually P of x, y. You know the function notation f of x?
Yes, sir.
That says it's a function of x. Well,
Yes, sir.
this says that profit is a function of x and y.
Yes, sir.
So it's written like this, P of x comma y. If it were a
Okay.
function of three different variables, it would be P of x comma y comma z. But this tells
Yes.
you what variables you're going to find on the other side of this equation, x and y. So
Yes, sir.
the profit we're going to make if we buy 0 cheap computers and 0 expensive computers is 0.
Yes, sir.
So that's probably not an answer. Now let's check this answer up here. That is P of 0 comma 175. Right?
Yes, sir.
Well, what's that profit?
So we
Have your
plug
calculator
it
handy? I think
in. Let
that's
me get my calculator.
875. Yeah, you should get a calculator. Always have it in front of you.
All right. So we have
No, it's not.
70,000.
What is 50 times 175?
50. Oh, 50. That's right. 175 times 50. 8,750.
So far, that's our best result.
Yes, sir.
Now let's check this vertex, or vertice, I guess. Okay, what is that? That is P of...
So would we need to do a system of equations?
Well, we need to figure out what that x coordinate is.
Yes, sir.
And that x coordinate comes from setting y equal to 0.
Yes, sir.
So that x coordinate is 250.
All right.
So I want to find out what the profit is when I buy 250 of the cheap machines and 0 of the expensive machines.
Oh, wait, you're doing the top. Okay, I thought you were doing the intersection of the two lines.
Not yet. That's going to be the last step because that's the hardest.
Okay, yes, sir.
And it isn't always the maximum. The maximum sometimes is on the side vertices. But
All right, so
what's 45 times 250?
11,250.
Well, so far that's the best answer. Now, no, Jesus. I can't believe. There we go. Here, let me erase some of this stuff. I want to erase all of this down here. How do we find out what the x and y coordinates of this point right there is?
Take the system of equations, set them both equal to y, and then set them both equal to each other.
Actually, just set them equal to each other. In other words,
Yes.
This line that has the -1 slope is this equation. The other line that has a slope less than -1 is that equation. So, yeah, actually you said it right. Solve for y and then set them equal to one another. Well, all right, so I've got y equals -x plus 250.
That's right.
Down here I got y equals -250x over 400 plus
That can be just 0.625.
700 over 4.
175.
Yeah, let's go ahead and write 175 there.
And then we can set those equal to each other.
Right. Now I'm going to set that equal to that. And that gives me where these two equations, each of these is the equation of a line. And
Yes,
it's
sir.
almost always going to be that way with linear programming, is all of these are going to be straight lines, at least at
Yes,
the
sir.
level you're at. I suppose it's possible that you could have quadratics that are parabolas in there, but you're always looking for where they intersect, because that's where these vertices happen.
Yes, sir.
All right, so if I set minus x plus 250 equals minus 25/40 x plus 175. Let's move this x to the right side and the number to the left side. So that gives us 75 equals 15/40 x.
Yes, sir. So
what does x equal?
x is equal to 200.
So the coordinates on that point are 200. And we need y also. So y must be 50.
That's right.
So now we plug in that x and y value into our objective function so that we're trying to calculate, where can I write it here? I'll write it down here. The profit when x is 200 and y is 50.
Yes, sir.
That is 9,000 plus 2,500, 11,500. Since we're looking for the maximum, that's it. We're comparing 0 with 8,750 with 11,250 with 11,500. So if this computer dealer buys exactly 200 of the cheap machines and 50 of the more expensive machines,
yes, sir,
he will spend exactly 70,000, and he will make the most amount of profit, 11,500.
Yes, sir.
As opposed to spending all of his 70,000 on the cheap machines, which would only give him this much profit, or if he spent his entire 70,000 on just the expensive machines, I got it backwards, he would get that profit.
Yes, sir.
But it's that other vertex that gives him the optimum. And what linear program basically tells you is that your profit maximum will never occur on the line like that, or it will never be right there. In other words, it has to be at a vertice.
Yes, sir.
And that's really the key. In other words, if you couldn't make that statement, you couldn't solve these problems. And that's why we only examine the vertices.
Yes, sir.
We know the maximum of that objective function is never going to lie between vertices. It's always going to lie on the vertex.
Yes, sir.
All right. So that's one of them. And the most difficult thing on these is really setting them up.
Yes, sir.
So let's see if we can set up 18.
All right.
Just on top of this page. And let's not worry about solving it as much as setting it up. I think once we set it up, you will realize that you can solve all of them. Okay?
Yes, sir.
All right. So if we read through this thing, we realize that we're trying to maximize profit again. Wait, hold on. right here.
Yes, sir.
So we're trying to maximize profit, which means we need an objective function that is the profit function.
Yes, sir.
So what do you think our variables are and what do they mean?
So our variables are going to be A and B, or yes.
Yeah, well, let's be a little bit more specific.
For
Let's call X the number of acres of crop A.
there we go. Okay. And Y the number of acres of crop B.
Yeah. And the reason it's so important to spell those out is because if you just say A is number of acres or X is crop A, is X the price of crop A or is it the number of acres of crop A? And it's almost always you can have a question like that. Even if you're selling Pepsis and popcorn at a movie theater, your variables are not Pepsis and popcorn. They're the number of Pepsis you sell and the number of popcorns you sell. And they're not the price of the Pepsi or the price of the popcorn. So there's lots of things it can mean. And that's why it's very important to spell out that you're dealing with X as the number of acres you're going to plant of crop A and crop B.
Yes, sir.
So this is a little bit more complicated one.
So we have, could we set up that X plus 2Y, or hold on, there are 250 days for trimming. Okay, so X plus 2Y must be less than or equal to 240. Is that one equation that we can use, or one inequality that we can use?
Yeah, I think so. I tend to want to take it from the top.
Okay.
So X plus Y is less than 150, right?
Yes, sir.
That's one equation. Excuse me, that's one constraint.
One constraint.
These are called the constraints. They're not usually equations, they're usually inequalities. Always.
Yes, sir.
Not usually, but, well, can't say always, but, okay. So we start there. Now, it takes 1 day to trim an acre of crop A and 2 days to trim an acre of crop B.
Yes, sir.
240 days per year available for trimming. So what inequality does that give me? I think you had it before.
So X plus 2Y must be less than or equal to 240.
Another linear equation. In other words, that's going to plot as a straight line. That's going to plot as a straight line.
Yes, sir.
All right. Now, it takes 3/10 of a day to pick an acre of crop A and 1/10 of a day to pick an acre of crop B. And there are 30 days per year available for picking.
So 0.3x plus 0.1y is less than or equal to 30.
Yeah, so if you had 10 acres of crop A, it would take you 3 days to pick them. All right. Find the number of acres of each fruit that should be planted to maximize profit. Okay, so we need a profit function. Our profit function as a function of x and y is what?
140x plus 235y.
And there you have it.
Oh, all right.
In other words, now what we're going to do, it's going to be hard to see because I'm writing on top here. But here, let me change colors. Will make it a little helpful. So I'm going to plot this first equation. Here, let me put some numbers here. Let's call that 30. Let's call this 150. And let's call this 240. Okay. So this first constraint is y equals negative x plus 150.
Yes, sir.
The slope like that, 45-degree slope. The second equation is y equals negative x over 2 plus 120.
That's right.
Well, negative x over 2 is negative 1/2. That's a flatter slope. The slope of my first red line is minus 1. Negative 1/2 is something like that. Okay?
Yes, sir.
And now the third equation, I've got y equals, let's see, I got 0.1y equals negative 0.3x plus 30. So y equals negative 3x plus 300. Okay, so if I go up to the y-intercept at 300, and this has a steeper slope, minus 3, so this slope,
yes, sir.
I don't know if it goes through that other intersection point or not. Okay, and
yes,
notice I've written all these as equations, but in reality they're inequalities.
Yes, sir.
And so,
and you would
yeah,
shade them
if I want to
accordingly.
shade a region that represents all the possible solutions, it would be this region right here. And I want to check this vertex, and this vertex.
Yes, sir.
I want to plug in those x and y values into my profit function and then figure out which one gives you a maximum.
Yes, sir.
Now, this is going to be a little bit tricky because I got to find this intersection point. And that usually is the answer. It's almost never the origin, and it's not usually one of these x coordinates and y coordinates.
Yes, sir.
But let's just plug in the x and y coordinate. In other words, let's figure out what profit of 150 comma 0 would be. And what that means is you're going to plant all 150 acres with crop A.
Yes. Yes, sir. So that'd be 140 times 150. 21,000.
Let's see what we would get if we planted all crop B. In other words, the profit of 0 comma 150.
So that's 35,250.
So that would be better than planting all crop A.
Yes, sir.
Now, tough part.
So there's a possibility that there are two intersections, at least.
Yeah, they definitely are. I've drawn it such that that line goes through the same intersection point of the other two, and that's not likely.
So we can just do a system of equations for the two.
Yeah, in other words, let's assume that that steep line, the line that has the slope of -3, doesn't go through the intersection of the other two. Let's assume
Yes,
it
sir.
goes, man, I know this is going to get hard to follow. Let's assume that it goes something like this. Okay.
Yes, sir.
Now that would give us different vertices to look at.
Yes, sir.
In other words, then we would have this vertex, and we would also have this vertex. So
Yes,
it would
sir.
actually give us two different vertices. And we want to check both of them.
Yes, sir.
So what we have to do is to set this equation equal to that equation to figure out where one of those vertices is. And then we have to set that bottom equation equal to the top equation to figure out where the other vertex is.
Yes, sir.
Then we're going to have two more vertices that we're going to be able to test on the objective function, and whichever answer gives us the most dollars is our answer.
Yes, sir.
Now, we can do that. That'll take us some time, especially since I'm going to have to erase some stuff and memorize some stuff. I don't know what's going to be more beneficial to you, which is to go through this whole problem completely, or go to another problem and set it up, because it's the setup that's the tough part.
We can go and set up another problem.
I think that's probably the thing we should do, because at this point it's just algebra trying to solve.
Yes, sir.
The key thing is you have to find out where that, in other words, where if I call these inequalities 1, 2, and 3, let's make that 1, that 2, and that 3. So this inequality, or excuse me, the blue dot that I've got as an intersection point is
Yes, sir.
the dot you get when you set equation 2 equal to equation 3.
Okay.
Solve both of them
Yes.
for y, and then set them equal to one another, and it gives you that blue dot. Okay? But there's
Yes,
another
sir.
possible blue dot right there, which is what you get when you set equation 3 equal to equation 1.
Yes, sir.
So that's another set of x and y coordinates. So we have 4 coordinates that we have to test. Those 4 dots. Now, the dot on the y-axis is easy to figure out because you know x is 0, so that has to be 150. The dot on the x-axis is easy to figure out because you know x is equal to 0, so y has to be 150. Or
Yes,
excuse
sir.
me, we used the right equation. I wasn't using the right equation. The only 2 dots that are difficult to figure out are the 2 dots that aren't on the axes.
That's right.
And you just have to make sure that you're using the right equation. In other words, that dot comes from those 2 equations. Those 2 equations are equations 2 and equations 3.
Yes, sir.
Solve each one of them for y, set them equal to one another, and that will give you the x and y coordinate on that point.
That's right.
Same thing for this dot up there, you're going to set equation 3 equal to equation 1.
Yes, sir.
Basically.
You're finding the intersection value.
Yeah, exactly. You know how to find the intersection between two linear equations.
Yes, sir.
And that'll give you an x and a y value. And
Yes,
plug both of those into your profit equation, and whichever one creates the most profit, that's your answer. And that's how you do all of these. Okay? And the only difference is some of them have 5 sides, some of them have 4. This figure that I've drawn in there has 5 sides. Has that side, has that side, has that side, has this side, and has that side.
Yes, sir.
So there's 4 vertices you need to check in terms of which one provides the most profit. And
Yes, sir.
I'm going to say that you cannot rule out the answers on the axes. In other words, you do have to try those. It is possible that your maximum profit would come from planting all crop B, which
Yes,
would be this one down here. Or excuse me, it would be this point up there.
Yes, sir.
All right. So we will ignore the algebra on this and see if we can set up another one. It's the setup that's tough.
Yes, sir.
All right. Let's see if you can do all of it here.
Flour mixes 2 brands of kettle feed. Brand X costs 25 per bag and contains 2 units, 2. Okay. Brand Y costs 20 and contains 1, 9, and 3. Find the number of eggs of each brand that should be mixed to produce a mixture having a minimum cost per bag. So we're trying to find a minimum here.
Right.
The minimum requirements of nutrients A, B, C.
Let's start with defining our variables. Always start there.
All right. So we'll have X is the number of brand X bags.
Let's see. It wants to know, find the number of bags of each brand. Okay. So number of brand X. Y.
It's the number of brand Y.
Number of bags of brand Y. Next, that's the only 2 variables.
Yes, sir.
Okay. Even though they give us an A, B, and a C, that's going to involve more constraining equations. But
yes, sir.
In terms of profit, let's see. We're not looking to maximize profit. We're looking to minimize cost per bag. So let's talk about a cost function.
So the minimum cost is equal to, the cost is equal to 25x plus 20y.
Okay, there's my objective function.
Yes, sir.
Now, constraining linear equations here.
Okay, so we have, let's find the restraint for element A. So 2x plus 1y should be greater than or equal to 12.
hold on a second. I'm still trying to get a handle on how we're going to treat these nutritional elements. We've got three elements, A, B, and C.
Yes, sir.
One bag of X contains 2A plus 2B plus 2C.
Yes, sir.
One bag of Y contains 1A plus 9B plus 3C. The minimum requirements of nutrients A, B, and C are 12, 36, and 24. So I've got A has to be equal to or less than 12. B has to be less than and equal to 36. And C has to be less than or equal to 24.
Yes, sir.
I think that might do it. The only thing is,
But you're trying to find
got something wrong here. Yeah.
the amount of A is going to be the sum of the number of the two bags.
So the amount of A would be 2 times 25.
Wait, would it be 2x? Because we're doing the number of bags?
Yeah. Let's go back and rewrite these three equations here. I think you're on the right track. The total amount of element A is equal to 2 times x plus y, correct?
Yes, sir. And we can already set that as an inequality.
If you had one bag of A and one bag of Y, you'd have 3 units of nutrient A. Okay, the amount of B is 2x plus 9y, and the amount of C is 2x plus 3y.
3y.
Okay, that's for sure. And then we have A plus B plus C. No, excuse me.
Would we set the
Yeah, each one.
would
A
we set them?
has to be less than or equal to 12. B has to be less than or equal to 36. And C has to be less than or equal to 24.
So we can combine those, right? So it can be like 2x,
so 2x plus y has to be less than or equal to 12. Yes, you're
right.
Right.
Greater than or equal to 12, right?
Well,
Since
we're going to graph it as we're going to graph it as an equation.
All right.
So I don't know that we have to determine that yet. In other words, that's going to be equal to 12, that's going to be equal to 36, and that's going to be equal to 24. So
yes, sir.
Those three equations are all straight lines.
Yes, sir.
They can be graphed just like we graphed all the others.
That's right.
They will produce probably 5 or 6 vertices.
Yes, sir.
We can solve for the vertices just by equating the proper equations.
That's right.
And each of those vertices is going to have an x and a y. We're going to be able to plug it in to this equation, our objective function. And whichever one gives us the lowest cost, that's the one we're going to pick.
Yes, sir.
Now, here, I think we've got it all right. Let's just see what this might graph as. And I'm not sure you absolutely have to draw the graph. In other words, I could figure out what the intersection points are going to be.
Yes, sir.
However, if I graph equation A, what do I get? Not A. I get y equals minus 2x plus 12, right?
Yes, sir.
So that equation, if 12, put 12 right there. It's a steep slope. It's a minus 2 slope. So that's that. And if I graph that second one, I get y equals minus 2/9 x plus 4.
Yes, sir.
That's going to go through the y-intercept of 4, and it's going to be a much flatter slope. 2/9 is something like that.
Yes, sir.
And finally, if I graph the third one, I get y equals minus 2/3 x plus 8.
Yes, sir.
That is a slope between these two slopes. That first slope was minus 2. What is this? 2/3. So this one, something like that.
Yes.
Now, I believe we have these intersections. Here's our vertices. There's one. There's another. Excuse me. There's another, and there's another. Cross out that first one. That's not a vertice. Not according to my drawing. I think
Wait, but if we're trying to
these 3 blue dots to check.
would it even be necessary to check the blue dot in the middle? Because if that does not satisfy the requirements of the
If we look at the objective function, that actually looks like it would be the answer. Notice that we're trying to minimize cost. And that has the lowest x value and the lowest y value. So I got to believe that's the answer.
does that
Now, the question is this our area that we're interested in? And I believe it is. In other words, that's not an answer right there. That cost is 0 at the origin.
Yes, sir.
But it doesn't satisfy the constraints.
No,
We
sir.
have to have a minimum requirements of A, B, and C that are 12, 36, and 24. And if we use this point at the origin, we don't get any nutrients. So we don't satisfy that other equation.
Yes, sir.
So that's convincing me that we do want to look at just the area that I've shaded in blue. That is our triangle that is going to produce the answer at one of those vertices.
Yes, sir.
And again, you would have to find the x and y coordinates of each of those 3 vertices. and plug them in, but unless my drawing is way off, it's definitely this bottom one, because I can see that has the lowest x value and the lowest y value. I can see it visually.
Yes, sir.
So that bottom one, let's just do that step. That is where I am combining equation B with equation A, right?
Okay. Yes, sir.
Yeah, that's B. In other words, that had a y-intercept of 4, and equation A had a y-intercept of 12. So if we set A equal to B, we got 2x plus y equals 12. And we have 2x plus 9y equals 36. I can solve this better by elimination.
Yes, sir.
I'm going to subtract the top one from the bottom one to get 8y equals 24, y equals 3. And if y equals 3,
So that means x is 4.5.
4.5, yeah. X is 4.5. So I would plug in 4.5 for x, 3 for y, and that would give me a cost of approximately $112.50 plus 60, which is $172.50.
Yes, sir.
I'm trying to find the number of bags of each brand that should be mixed to produce a mixture having the minimum cost per bag. So the cost of this bag would be whatever number I just came up with.
25 times 4.5 plus 20.
That's $112.50 plus 60. That's $172.50.
Yes, sir.
So that's the cost if I do this point here. This point here, notice, has a smaller x.
Yes, sir.
So I was wrong when I originally said that that lower left point of that triangle was the lowest x and the lowest y. It's not the lowest x. It's the lowest, it's not even the lowest y. This is a lower y over here.
Yes, sir.
Okay, so I actually do have to figure out all three of these vertices, input them into the objective function, the cost function, and figure out which gives me the lowest cost. And that'll be the answer.
Yes, sir.
And yeah, it's not clear at all from this picture which one is going to be. And unless we go through and do all the math, we're not going to be able to solve it, but that's going to take quite a bit of time. Time did we start?
Yes, sir. I think 6:35.
So we've been going for an hour?
Yes, sir.
All right. You think you get it? I think you do.
I think so. I think so.
Yeah. And you can see
it makes
that
sense.
the toughest part is setting up all of these, setting up
That's
the
right.
objective function and setting up all of the constraining inequalities, graphing them, figuring out where your vertices are, plugging those into the objective function.
Yes, sir.
That's the name of the game. And this is what they start out brand new Algebra 2 students on.
Wow.
Amazing, isn't it?
Wow.
Because I can't think of a single thing in Algebra 2 that's harder than this.
Really? Wow.
Not one. Very first Algebra 2 student I ever had, this is what she hits me with at the first day. I don't have a
Wow.
clue how to do it.
Whoa.
Well, I didn't see her a second time, but I did go home and learn how to do these.
Wow. Well, that's good.
It's
Well,
funny how often that actually happens, where when you see a new student, they always hit you with the toughest problem. They don't give you their easiest problem.
that's right.
So if you can't do the toughest problem, you're in a world of hurt.
Yes, sir.
But anyway, that's how you do these.
Yes, sir.
So Garrison, how much longer are you in school? When are you gonna? Oh, you were out before the last week of May, aren't you?
Yes, sir.
Which means we don't have much time left, huh?
That's right.
A week or two.
Around a week and a half. Yes, sir.
And then is the plan still to learn calculus over the summer?
Yes, sir. PreCalc.
All right. To be perfectly honest with you, there isn't a whole lot in PreCalc.
Oh, okay.
It really isn't. There's a lot that they teach you. It can be a full semester of PreCalc, but PreCalc kind of covers trig, covers a few other obscure things that you need for calculus, but not really. What you really can do to teach somebody calculus is if they know algebra, geometry, and trig, you take those three maths, you combine them with the concept of limits, and you have calculus. And so where I'm going to start is with limits. I'm going to assume you know algebra, geometry, and trig well enough, and we'll find out if you do or not as we go through.
Yes,
but the most important new concept that you learn with calculus is limits. There's nowhere else in math where you learn limits until you hit calculus. And that's what really throws off most people, is that concept. Not just most people, but famous mathematicians. There's a calculus theorem called Raleigh's theorem. And Raleigh was a mathematician that went to his grave not accepting calculus. He didn't believe in this limit thing. He never really believed calculus was valid, and yet they named a theorem after him.
Wow.
So it's kind of funny. But anyway, that will be the plan, the game plan.
Yes, sir.
All right. I will let you go. And hold on, let me just check to make sure I got the schedule right for next week. Oh, let's see. We have another session on Friday at our normal time.
Yes, sir, we do.
Okay. So that's when I'll see you next.
Yes, sir.
All right. Garrison, have a good evening, and I'll talk to you on Friday.
Yes, sir. See you then.
Bye-bye.